Mixtures of gases. It's very common to have gas samples that are not a pure gas, but they're mixtures of gases. Air is a great example. So what we call dry air, 0% humidity, is a mixture that has nitrogen, oxygen, argon, carbon dioxide, and then a few other gases in there as trace amounts. And so dry air is 78% by volume nitrogen, 21% oxygen, 0.9% argon, and 0.04% carbon dioxide. So it's mostly nitrogen and thankfully a good amount of oxygen. Turns out this is the perfect amount of oxygen for humans to breathe. So sometimes we can treat a gas mixture as though it were just a single gas. When we look at a sample of air, we can measure the pressure, the volume, the temperature of the air, and do calculations with that as if it were a pure substance, even though it isn't. And the reason we can do that is because gas particles behave independently, and the identity of the gas is not important. So Dalton's law of partial pressures helps us to understand how a mixture of gases behaves. So in a mixture of gases like air, you have nitrogen and oxygen. The nitrogen behaves like it's the only gas in the container. The oxygen behaves like it's the only gas in the container. And so we can talk about a partial pressure. So for any one gas in the mixture, it's going to have its own pressure that it exerts. And that pressure is going to depend on the number of moles of the gas, the volume of the container, and the temperature. And so we could calculate the pressure due to a single gas, just some gas N. It'll be the number of moles times RT over V. That's the pressure for one gas. Dalton's law of partial pressures says that the total pressure of a mixture is the sum of the pressures of each individual gas. So this is a little bit like looking at a box of fruit. I'm going to write this down because otherwise I'm going to forget. And let's say we have 3 pounds. I keep writing with the wrong end of my stylus. Both ends are supposed to work, but they don't. Let's say we have 3 pounds of apples, and we have 2 pounds of oranges, and 5 pounds of bananas. Does the weight of the apples depend on how many oranges or bananas are in the box? No. It depends on how many apples are in the box. The amount, the number of molecules, the number of apples, the number of oranges affects the mass of the oranges. What's the mass of the whole box of fruit?
All of that.
You just add them together. 3 plus 2 plus 5, 10 pounds. Each gas exerts its own pressure. Because they're I guess you could think of them like being ghosts, right? They can go through each other. It's mostly empty space. And so you've got these particles, and they're just all mixed together, but each gas is exerting its own pressure. The total pressure is the sum of all the pressures of the individual gases. Any questions about that? It's kind of an odd idea. So this chapter has some math derivations in it, which, if you like that sort of thing, it's really cool, and if you don't, your eyes are just going to glaze over. So I'll just go through this real quick for those of you that might be interested. So the total pressure is the sum of the pressure from each gas. The pressure of gas A is going to be the amount of moles of gas A times the ideal gas constant, the temperature, and the volume, right? We just saw that over here. If you just solve the ideal gas law for pressure, that's what you get. And for gas B, it's going to be the moles of B times RT over V. These gases are together in one container. They all have the same temperature. They have the same volume. So gas C, moles of C times RT over N. So we can factor RT, I said N, RT over V. We can factor RT over V out, and then we've got moles of A plus moles of B plus moles of C, etc. We could combine those terms and say, well, that's the total number of moles of the gas. So the total pressure is equal to the total number of moles times RT over V. The ratio of the partial pressure of a single gas to the total pressure, so the partial pressure of gas A to the total pressure, I guess you could call that like a pressure fraction, is going to equal the mole fraction. So the pressure of gas A is moles of A times RT over V. The total pressure is the total number of moles times RT over V. The RT over V cancels out, and we've got moles of A divided by the total number of moles. That's called the mole fraction. So if we multiplied by 100, it would be the percent, but we're not multiplying by 100. So moles of A over the total number of moles. So this is the part over the whole, but instead of doing it in grams, we're doing it in moles. And this is given the symbol chi of A. So it's a kind of a curvy big X. It's not an X though. So taking this without the junk in the middle, PA over P total equals NA over N total. We can rearrange that for PA. You get this, and then plug chi of A in for that term, and that's how we end up with this. And there's the bottom line. If the rest of that was just like Charlie Brown's teacher, wah, 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 you know, okay, this is, you can open your ears again now. That's what we want to get to. So that and this. The pressure exerted by gas A in a mixture is equal to its mole fraction times the total pressure. The mole fraction is just the moles of that gas divided by the total number of moles. It's like a percentage divided by 100. For gases, the mole fraction is equivalent to the percent volume divided by 100. So we said in the opening slide for this section that the air has a composition of nitrogen that's 78%. Air is 78% by volume nitrogen. 78% by volume, 78% corresponds to a mole fraction of 0.78. So that's chi for N2. So the pressure exerted by nitrogen is 0.78 times the total pressure. Well, atmospheric pressure is about 1 atmosphere, right? So 0.78 times 1. The pressure of nitrogen in the air that we're breathing is 0.78 atmospheres. Any questions? Let's look at a problem. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. A chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15.0 grams of neon, and 35.0 grams of krypton in a piston cylinder assembly at STP. Calculate the partial pressure of each gas. That's kind of a leap, isn't it, from what we were talking about? What the heck? Well, let's think about what we've learned. Partial pressure. The partial pressure of a gas, so let's maybe talk about helium first. The pressure of helium is going to be the moles of helium times RT over V, nRT over V. right? Well, could we calculate the moles of helium? Yeah, they gave us mass, but we could convert mass to moles. Well, let's try that. So 5.50 grams of helium. We need the molar mass. We look at the periodic table. 1 mole of helium weighs 4.003 grams. So 5.5 divided by 4.003 equals 1.37. I want to keep 3 sig figs. And then 397 moles of helium. Okay, so this is good. So I've got N. I know what R is. What's T? The temperature. What is the temperature in this problem? It's STP, so it's 273.15 Kelvin. What's the volume? They didn't give us a volume. Shoot. How can I calculate the pressure if I don't know the volume? Well, this is a mixture of gases, right? Each gas, helium, neon, and krypton, are exerting a pressure on this container, and their pressures add up to what? The total pressure, in this case, 1 atmosphere. So we're still maybe a little lost, right? I'm trying to demonstrate how you work through this. Because, I've been teaching this stuff for a long, long time. But when I do a problem like this, it does not just jump out and say, oh, you need to do this, this, and this. Some of these problems I have to think about, okay? And so I expect that you would have to think about them more, and that you might have to puzzle over them. So I'm puzzling with you. So the total pressure is going to be equal to the pressure of the helium plus the pressure of the neon plus the pressure of the argon. And we know that that's 1 atmosphere because it said at STP. Okay, so that's all very fine. But I have 3 unknowns, so that equation by itself isn't going to help me. What else did we learn about? This one. The pressure of A is the mole fraction of A times the total pressure. Do we know the total pressure? Yeah. Could we calculate the mole fraction? Yes. That's what we need to do. So what we need to do is, for helium, the pressure of helium is going to equal the mole fraction of helium times the total pressure. Mole fraction is the moles of helium divided by the total moles of gas. So we have to find out how many moles of gas there are. So we already did helium. We need to do neon, 15.0 grams of neon. Molar mass of neon, 20.18 grams per mole. Zero 0.743 31 moles of neon. And then we need to calculate the moles of krypton. 35.0 grams of krypton times 1/83.80. 0.41766 moles of krypton. So mole fraction of helium equals the moles of helium divided by the total number of moles. I know the moles of helium, I need the total number of moles. So I'm going to add those together. 1.37397 plus 0.74331 plus 0.41766. So N total is 0, no, not 0, that wouldn't work. 2.53494 moles. What digit is the last significant digit? The 3. When we're adding, we're looking at decimal places. This number has 2 decimal places that are sig figs. This one has 3, this one has 3. And so since there's uncertainty in the second decimal place in one of the results, I need uncertainty in the second decimal place in my total result. So the mole fraction of helium is equal to the moles of helium, 1.37397, divided by the total, 2.54, what? Not 5349. So this is moles, and that's moles. What happens to the units? They cancel out. So my mole fraction here, 1.37397 divided by 2.5349. My mole fraction is 0.54202. No unit. The pressure of helium is my mole fraction times the total pressure. The total pressure is 1. So I just need to take that and multiply by 1 atmosphere. So the pressure of helium equals 0.5402 times 1 atmosphere. So 0.542 atmospheres. For helium. We still need to do neon and krypton.
How did you get from the pressure of helium, then from the second step?
How did I get this?
Yes.
So that's the definition of mole fraction.
Okay.
So it's the moles you're interested in divided by the total number of moles. It's the part divided by the whole thing.
Is that what we went through?
Yeah, that's on 2 slides ago,
Okay.
near the top of that slide. And so I calculated that, and I got a result. And then here I'm putting mole fraction and total pressure back into the equation up here. So we need some space. We'll make some space. So similar thing for the other gases. So the pressure of neon, the partial pressure of neon is going to be the mole fraction of neon times the total pressure. So the mole fraction of neon is the moles of neon, 0.74331 moles, divided by the total number of moles, 2.5349 moles. 0.293. 23, that's the mole fraction. So then I go up here, and it's the mole fraction times the total pressure. So this is 0.293 atmospheres for neon. What's the pressure of the krypton? Do I have to do all of this? I can do all of this. It's going to work just fine. I can subtract them. So we know that the total pressure is the pressure of each of these gases added together, and it's 1 atmosphere. I figured out what 2 of them are. I can get the third one by subtracting. So if I take 1 atmosphere and I subtract this one, and I subtract that one, that's the pressure for krypton. Let's maybe do this in a different color. So the pressure of krypton is 1 atmosphere minus the pressure of the helium, 0.542 atmospheres, minus the pressure of the neon, 0.293 atmospheres. 1 minus 0.542 minus 0.293 equals 0.165. If we think back to the box of fruit, if I know the total mass of the box and I know the mass of the apples and the bananas, I could find the oranges by just subtracting. That's all I'm doing here. If you want to calculate the mole fraction and put it into this equation, that'll work too. Any questions? Okay, here's another one. A sample of hydrogen gas is mixed with water vapor. So this is not a dry gas, this is what we call a wet gas. Because what makes a towel wet? It's got water in it, right? So if a gas has water vapor in it, then it's considered a wet gas. The mixture has a total pressure of 755 torr, and the water vapor has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 Kelvin? Again, it's not necessarily obvious what we should do, right? But we do have a mixture of gases. We've got hydrogen gas and we have water vapor. So our total pressure is going to equal the pressure of the hydrogen gas plus the pressure of the water vapor. Do we know any of those? We do. They told us what the total pressure is. So the total pressure is 755 torr. And the water vapor has a partial pressure of 24 torr. Could we figure out the pressure of the hydrogen from that? Yeah, all we have to do is subtract. (731 torr), that's the pressure of the hydrogen gas. Okay, so that's nice. We found something out, but what are they asking us for? Moles. Moles of hydrogen. Well, we've got a pressure. That's very nice. What else do we have here? We have a volume, 1.55 liters, and we have a temperature, 298 Kelvin. We're looking for moles. We're looking for N. What equation do we need? Ideal gas law. PV equals nRT. So that is rearranged to N equals PV over RT. Can we use this pressure as it is? Now we have to convert to torr, from torr to ATM. So it's 731 divided by 760. 0.9896. 1, here's my 3 sig figs, 84 atmospheres. So that goes into my equation. It's the pressure, 96184 atmospheres. What's the volume? 1.55 liters. I don't need to change that unit because it's already the correct one. Here's our friend, the gas constant. 0.08206 liter atmospheres per mole Kelvin. And my temperature has to be in Kelvin. It already is, so I put it down there. So I've got 0.96184 times 1.55 divided by 0.08206 divided by 298 equals 0.060966. And when I cancel out units, liters cancel, kelvins cancel, atmospheres cancel, I end up with moles. So I've got 0.6. I'm keeping the place where the 9 is. I look at the next one, I have to round up. 9 rounds up to 10. So that rounds the 0 up to a 1, and then I need to write that 0 at the end there. 0.610 moles. Yes, 0.0610. Thank
We
you.
want you to have a bunch of hater comments on YouTube. later.
Right, yeah. I get some really weird comments. One I got yesterday, somebody called me baby. But there were also some other, like, there was a different alphabet in there also, so I think he was translating or using Google Translate, and it didn't come up well. Any questions? Deep sea diving and partial pressures. So when you breathe compressed air is at a higher pressure, right? That increases the partial pressure of each of the gases in the mixture. So when you breathe compressed air, you're breathing a higher pressure of oxygen, which leads to higher oxygen in your tissues. And you might say, well, that's a good thing, right? Well, to a point. You can have oxygen toxicity. You get a partial pressure above 1.4 atmospheres of oxygen, and it could actually kill you. So it's like with water. We need water to live, but too much water will kill you. We need oxygen to live, but too much oxygen will kill you. And that is the case with many different substances. So oxygen toxicity, too much is bad, too little is bad. Hypoxia, hype means low. No, never mind. We're not going to analyze that word. We're just going to go on. Hypoxia is oxygen starvation.
Well, hypo means low.
Yes, hypo means low. That's what it was. Hyper. Okay.
You had it.
Yeah, it's a glitch there. It's fine. Every once in a while, I just kind of freak myself out. So if you're breathing compressed air, you're getting more oxygen. You're also getting more nitrogen. So at the surface, total of one atmosphere pressure, you've got 0.78 atmospheres of nitrogen, 0.21 atmospheres of oxygen. If you go 30 meters below the surface, in order to be able to breathe, your pressurized gas needs to be at 4 atmospheres. You're going to have 3.12 atmospheres of nitrogen and 0.84 atmospheres of oxygen. The oxygen is going to be okay. It's not over that toxicity level, but the nitrogen's pretty high. And then too much nitrogen is bad for you as well, and causes what's known as nitrogen narcosis, or rapture of the deep. It has symptoms similar to alcohol intoxication. You can get drunk on nitrogen. You might say, well, why is that bad?
Yeah, how's
Well,
the hangover?
I don't know how the hangover is, but what does intoxication do to your judgment? It impairs it. So here you are, 30 meters below the surface, and you're not thinking clearly.
You know, that managing is starting to look real good.
You could do some stupid things that would get you killed, right? So you want to avoid nitrogen narcosis. So how do they do this? Well, you get a special mixture of gases. You put something in there so that you can reduce the mole fraction of oxygen and nitrogen. So here's a problem. A diver breathes a heliox mixture. So heliox is a mixture of, guess what? Helium and oxygen. Heliox mixture with an oxygen mole fraction of 0.050. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? We would like the oxygen partial pressure to be 0.21 atmospheres because that's what our bodies are good at using. That's what the pressure is at the surface. So how do we figure out what the total pressure is? You think of an equation that has partial pressure, total pressure, and mole fraction? The pressure of O2, the partial pressure of O2, will be the mole fraction of O2 times the total pressure. So let's think about, there's a sale, so just a sale that got the women, and we'll make it a sale at REI and hopefully get the guys in as well. You got 75% off something you've been really wanting. Okay, 75% off. So if the full price is, I don't know, let's say $200, if it's 75% off, how much what percent are you going to pay? 25. So you're going to pay 25%. How do you find out what 25% of 200 is? Well, 25% is 0.25 as a fraction, or 25 per 100. You do the math, it comes out 0.25. It's 1/4. 0.25 of this, 0.25 times 200. So how much am I going to pay? $50. That's a sweet deal. This equation is the same idea. The part that we're interested in, the 25% that we have to pay, is the fraction, the 25%, times the total, the full price. So if you think about what this equation means, it's really not that hard to remember. I'm going to get rid of all that. I have a little more time today, and so that's why I'm doing things like this, because I can. Normally I don't have time for that. So the partial pressure of oxygen, what do we want it to be? 0.21. So PO2, we want that to be 0.21 atmospheres. And the other information they gave us was that the mole fraction was 0.050, no units on that. And we're looking for total pressure.
But it's heliox with an oxygen mole fraction.
Yeah.
Not the heliox
the 0.05 is the heliox. Right?
No, it's the oxygen in the heliox. So the rest of it, the 0.950, would be the mole fraction of helium. So what I need to do is I need to take this equation and solve for total pressure. I divide both sides by the mole fraction. So the total pressure will be the partial pressure divided by the mole fraction. So 0.21 atmospheres divided by 0.050. 4.2. So the way this works in diving is that you have a heliox tank and you have an air tank. And then you have a regulator that allows you to combine those in different amounts. As you go down, you're switching from the compressed air over to the heliox so you can maintain the right oxygen level. Any questions? Chemistry in scuba diving. Gases are really neat to work with because we can figure out how many moles we have by measuring pressure, volume, and temperature. But they're also a pain to work with because they won't stay in a beaker. Right? You can't get a gas to stay in a beaker. It's going to escape and float all over the place. So we have to trap them, right? So you have a reaction maybe that's releasing a gas, and how do you catch the gas but not get any air? We do it by displacement. So we'll have a container full of water, and then we'll collect the gas in there, it will displace the water, and then we can trap the gas. But besides the gas we're interested in, we also get water vapor in there because the water will evaporate into that space. And so we're going to get a mixture of water vapor and the gas we're interested in. Since this comes up so often, they actually have a special term for the partial pressure of water vapor. We just call it the vapor pressure. So it's partial pressure of water. And this vapor pressure depends only on the temperature. So people have studied this, and you can look up in a table the vapor pressure of water at any given temperature you might be interested in. And here's such a table. This one gives increments of 5 degrees. You look in the CRC and you can get much smaller temperature increments. If I'm collecting gases, say at 25 degrees Celsius, I'm going to have a partial pressure of water that's 23.78 millimeters of mercury. As you increase the temperature, the vapor pressure of the water increases. So this is what it might look like to collect a gas. We call it collecting a gas over water. This is the gas we're collecting, and it's over some water. That's why we call it that. So here we've got our reaction, zinc and hydrochloric acid. Those are going to react and release hydrogen gas. The hydrogen gas is wanting to escape, so we give it a way to escape. It's going to escape through this tube, and we come over here where we have an inverted beaker in a dish of water. It's a little bit like the barometer, but it's water instead of mercury. And the gas will bubble through here, and as it fills this up, it's going to push water out. And so now we've got hydrogen gas plus water vapor. But if we're interested in the moles of hydrogen, we have to take into account that there's water vapor there as well. A sample of acetylene is collected over water. Anytime you see collected over water, think, I have to use partial pressures here. The total gas pressure is 738 torr. The volume is 523 milliliters. At the temperature of the gas, 23 degrees Celsius, the vapor pressure of water is 21 torr. How many grams of acetylene are collected? Well, we have a gas. Let's pull these numbers out and write them down. So 738 torr, that's the total pressure. The volume is 523 milliliters. The temperature is 23 degrees Celsius. The vapor pressure of water is 21 torr. So vapor pressure of water, that's a partial pressure. So that's the pressure caused by the water vapor. And we're looking for grams. Well, what does volume, temperature, and pressures make you think of?
Ideal gas.
Ideal gas law. What can we calculate with this information in the ideal gas law? Moles. So we could calculate moles, bless you, and then we've got the chemical formula here. We can find the molar mass and convert it to grams. So we're going to find the moles, and then we're going to find the grams. Okay, so the number of moles is PV over RT. So we need the pressure. They gave us two pressures. Pressure of water vapor and total pressure. So we have a mixture of gases here. There's acetylene and there's water. Which one are we interested in? The acetylene. We don't want the total number of moles. We want the moles of acetylene. We need the partial pressure of acetylene. So we're going to do that by subtracting. I guess I'll call it C2H2. The partial pressure of acetylene is going to equal the total pressure minus the pressure of the water. I think it's easier to do the subtraction in torr and then convert to atmospheres. So we've got 738 torr minus 21 torr. So we have that many torr, 717. Do you wonder why we keep using torr? And why not report all of these in atmospheres?
They just like to make us work extra hard.
They like to make you work extra hard. Actually, that's partially true. If we convert 21 torr to atmospheres, we get 0.0276. We end up with some very small numbers, and this is a nicer unit for reporting smaller numbers, smaller pressures, because it gives us numbers that are easier to handle. I think that's the main reason that we still do that. So there's our pressure of the acetylene we have to convert to atmospheres. So we take our 717 divided by 760. 0.94342 atmospheres. Okay, so there's our pressure. 0.94342 ATMs. And our volume, 523 milliliters. So I want to show you a different way to do this conversion. What if instead of writing milli, I write what it means? What does milli mean? 10 to the negative 3 liters. That's not standard scientific notation, but your calculator's still going to understand it. Or you can just punch it into your calculator and press equals, and it'll give you this. There's our volume in liters. 0.523 liters divided by I wish I had a rubber stamp I could use. 0.0826 liter atmospheres per mole Kelvin. Over and over and over again. And the temperature, 23 degrees Celsius. Okay, we got to convert that. So so that's going to be, let's see, 298 is 25, 296.15. Did I do that right? That's always dangerous when I do math in my head. So our pressure times 0.523 divided by the gas constant divided by 296.15 equals 0.020303 moles. I need to convert that to grams. I need the molar mass of acetylene, 2 times 12.01 plus 2 times 1.008. I'm not going to do that in my head. It sounds like a bad idea. 26.036 grams per mole. There I have my moles of acetylene, and then I'm going to use my molar mass as a conversion factor. Grams per mole. I'm coming up with 0.5286. Grams, and then I would round that to 0.529 grams. Any questions? I hope that's the last slide. Dang. We're just going to take a deep breath. We're going to do it. We're going to finish the section. The common way to make hydrogen gas in the lab is to place a metal such as zinc in hydrochloric acid. The hydrochloric acid reacts with the metal to produce hydrogen gas, which is then collected over water. Suppose a student carries out this reaction and collects a total of 154.4 milliliters of gas at a pressure of 742 millimeters mercury and a temperature of 25 degrees Celsius. What mass of hydrogen gas in milligrams does the student collect? Well, let's write down some numbers. We've got volume, 154. Yeah, wrong end of the stylus again. 154.4 milliliters. What do you think we're going to have to change that into? Liters. Let's just do it right now. 0.1544 liters. Pressure is 742 millimeters of mercury, and the temperature is 25 degrees Celsius. So do I just plug this volume, the pressure and the temperature into the ideal gas law? What do I need to fix first? I need to fix the units on the pressure and the temperature, but there's something else I need to fix. Collected over water. This is the total pressure, and it includes the pressure of water vapor. They didn't give me anything about vapor pressure of water. I'm supposed to know from the phrase collected over water. How do I find the pressure of the hydrogen gas? I need a table because I need the pressure of the water vapor so I can subtract it from the total pressure. So I need to find the table. The temperature is 25. So the pressure of the water vapor is 23.78. Sorry for the silence. I couldn't keep 23.78 in my head while I said 742 out loud. So the pressure of the hydrogen then is the total pressure, which is the hydrogen and the water together, and I'm going to subtract off the pressure of the water. I looked that up in a table. So I've got 742 minus 23.78. So just the hydrogen by itself is 718.22 millimeters of mercury. Sig Fig rules tell me that's 3. And I have to convert that to atmospheres. You feel like we keep doing some of the same things over and over and over again? We do. We do keep doing them over and over again. And so hopefully it'll stick. Atmospheres. And temperature, we have to convert that. It's going to be 298.15 Kelvin. So we're going to find the moles the same old way, PV over RT. There's the pressure, the volume, R.08206 liter atmospheres, mole Kelvin. And then the temperature, 298.15 Kelvin. So I get 0.0059638 moles of hydrogen gas. What's the formula for hydrogen gas? H2. Hydrogen is a diatomic element. Here it's by itself, so I need to convert that. It's 2.016 grams per mole. But what unit did they ask for? Milligrams. So I need milligrams over grams. Milli means 10 to the minus 3. I'm getting 12. 12.023. So 12.0 milligrams. Any questions? There's like an infinite number of problems that could be made up for gas law.